Good evening, everyone. Today we will continue with further properties of matrix exponential. We will go with a couple of propositions that we will prove here. So let's go into the first proposition. The first proposition tells us that we have a matrix with real coefficients, which is a simple matrix, a 2 by 2 matrix. And we need to suppose that this matrix has distinct eigenvalues whose real parts are less than a negative number alpha. This is important. And we need to show that every solution of this differential equation, for every solution of this, there exists a constant t naught which is greater than 0, such that the following holds. So we know that there are two cases that we need to consider. The first case is where the eigenvalues are real. Both of them are real eigenvalues, which are different by this condition. They are distinct eigenvalues. So in this case, let's say we have matrix A. Then we know by theory that the Jacobian of this matrix will have this form: lambda 1, lambda 2 in the diagonal, and 0 in the other positions. So this is the first scenario. The second is that lambda 1 is a complex number and lambda 2 is the conjugate of lambda 1. In this case, the Jacobian of the matrix A will be the following. The diagonal are the real part of one of these complex eigenvalues. Let's pick the first one. And this is minus the imaginary part of the same eigenvalue. So for the first scenario, we can analyze it pretty easily. Let's say psi is a solution of this system, which means that it can be written like this, with this one is the some initial value, which we don't need to know, but let's say that this is equal to some A and V. Then the theory tells us that this will be equal to some matrix, invertible matrix P minus 1 times the exponential of the Jacobian matrix times P times this one. So we know that, let's write it here, the exponential of t times the Jacobian of the matrix A is equal to the exponential of t gamma lambda 1 and the exponential of t lambda 2, and 0, this is a property. And from this, for the second scenario, this is equal to the exponential of the real part times, there's no space, let me make some room here. Alright, so this is the cosine of, well, let's write it like this. Let this be v, cosine of v, cosine of v, sine of v minus sine of v. So we know that. Then for the first scenario, let's go with the first one. This will be equal to this matrix like this, right? So when you perform these calculations, let's write it here, we are with real eigenvalues. This is a case that we are analyzing first. So when you perform these multiplications, whatever p and its inverse could be, and whatever initial condition, at the end of these multiplications, you will have something like this. So it can only be this way. We don't know which values are k1 and k2. They are real, of course. Let's write it here. But we don't know if they are positive or negative. And the only thing we know that is that the solution has this form. So now let's go to the thing that we want to prove. We want to prove that the norm of the solution is strictly less than the exponential of alpha times t for every t that is greater or equal than t naught. So let's start with some conditions like this. This is of course equal to, let's call the first entry sub 1 and the second entry sub 2. So this is equal to square plus square. Oh well, we can write it like this. And we know by the triangle inequality that this is less than this one plus this one. So this is clear, and this will be less than equal than. Now we write the coefficients here. Plus and the other. So we apply the triangle inequality once again, and we have, let's write it like this. Plus, you know that this is always strictly greater than 0, so the absolute value is the same. And now you also know that the exponential, the real exponential, it's a monotonous function, strictly monotonous, which you can draw like this. Then it is by the problem tells you that gamma 1 and gamma 2 are some negative numbers which are less than some alpha, which is also negative. But since the exponential is strictly increasing, then either the exponential of t alpha 2 will be greater than the exponential of t alpha 2, of course, for t greater than 0. Right. Or it will be the other way around, whatever is greater than from these two. And in every case, let's put it, in every case we can define some gamma 3, which is the maximum of these two. So we can say that let's call this just some constant 1 and this is a constant 2, which are like this. So this will be the constant 3 plus, oh wait, you can just put it like this, right? Nothing wrong with this. So now, since this lambda 3 is the maximum of these two, and these two in turn are strictly less than alpha, then it follows that this one is strictly less than and let me put it in yellow like this. So you know that we can do this only because this term is either 0 or positive. So it's the only reason why we can write this. And now we somehow need to find some t sub 0 such that for every t that is greater than this, we will have that this is strictly less than, so it's like we are almost there but not really there, because we have this coefficient which doesn't go away. So this is not quite the right way to do it. The right way to do it is the following. So let's put this it was okay until this point. So let's stop here for a moment. This is an important result. Let's summarize this. This norm is less or equal to this. Yeah, this is fine. This is okay. This is all right. So on the other hand, we have that is strictly less than this one. So since we have this, it follows that alpha minus is greater than 0, right? So we can write something like this. So we divide this. No, wait, it's the other way around. I mean like this. We don't want this. We want the other way around. It was looking quite weird there. So yeah, this is negative. So this function, since this is negative, this part is negative, then the limit of this is 0, right? So we can say that there exists some term like this such that for every it follows that this thing is less than this one. I don't put the absolute value because this is always positive. So this exists by definition of the limit. We are taking this as the epsilon. So let's just write like this. So at some point we will have that is strictly less than for every t like this, then we can write this like this one, and it is clear that then we multiply both sides by this term, and we are left with this expression for every t greater than t naught. So we replace this in this expression. Let me copy it quickly here. And so now we are working with t strictly greater than t sub 0. So this is strictly less than, and we copy it here. So this cancels. And yeah, this, why should we write it like this? So we are assuming that C plus C2 is different than 0, right? Otherwise this wouldn't make any sense. But let's scroll a bit. So both terms are greater than 0, and the only way they can be 0 is when both k1, k3 are 0 and k2 and k4 are 0. So only whenever the solution is trivial, right? When everything is 0 and the solution is trivial, then only in that case c1 plus c2 is equal to 0. But well, we were told that for every solution, well, if it's not a solution, I think it's not a solution because such a solution, such a trivial solution, we don't have distinct eigenvalues. So let me think about this for a moment. No, it's not needed because let's say we have a trivial solution where this is exactly 0, then 0 is always greater than anything like this, right? Because the exponential is always greater than 0. So in this case, t sub 0 could be any positive number. It wouldn't matter. So we are working in the case where this isn't a trivial solution. So everything follows, and we have proved it for the first scenario. Now let's go to the second one where lambda 1 is a complex number and lambda 2 is its conjugate. Let's copy this matrix. In this case it's simpler, I think. Second step. So you know that will be equal to this matrix, and this will be equal to this one. But since this is a scalar number that is multiplying a matrix, we can put it outside. So this will be times whatever the result of this matrix is, whatever it is here. We don't really care about this, I think. It will be a matrix, let's say A and V, and this will be equal to like this. Well, there's a missing T here, I think. Yeah, so these matrices are this thing will go to 0 as t grows into the positive infinity. And even though it's not showing, I think. Yeah, so even though this is also t and t, but you know that sine and cosine are bounded functions, so this is not a constant. This is some function of, let's say, phi of t, but phi is bounded. It's bounded because cosine and sine are bounded functions. So this thing is always bounded from, I don't know, some limits we don't really need to know. But this thing goes to 0. So everything goes to 0, tends to 0. So now we know that the real part of lambda 1 is strictly less than alpha, and we apply the same procedure as above, exactly the same. It's just that in this case there's no lambda 1 and lambda 2, it's only real of lambda 1, and we will arrive at the same t node. Well, not the same now, but the same. It will appear from exactly the same procedure. We will go with these inequalities, and then we will apply the limit, and so on and so on and so on. So the procedure is the same. Let's leave it like that. You can complete it by your own. And now let's go with the second proposition, which is, I think, a little more straightforward. the problems tell us that we are once again working with a square matrix, and we need to show that this limit is 0 for every solution. In this case, if and only if the eigenvalues of A have negative real parts. So we will apply this formula, this property. Let's write it here. If lambda is an eigenvalue and V is its eigenvector, then is equal to, let me highlight this. This is the property that we will use here. So it says that for every solution, then let's work with the solutions that comes from this initial value, where V is the eigenvector of some eigenvalue. Let's say V is lambda. And for every lambda, well, let's leave it like that. And then we know that is equal to, and then this is equal to, by the property, I think that is clear. So at this point, the limit of as t goes to plus infinity will be 0 if and only if, because you know this exponential is equal to t times the real part of lambda, and then the cosine of the imaginary part of lambda plus the imaginary unit times the sine of the imaginary part of lambda. But once again, this is bounded, and this is a constant. So everything depends on this exponential, which is a real exponential, and so this whole solution will tend to 0 if and only if the real part is negative. Because if it is 0, then this is 1 and this doesn't converge, I think. And if it's positive, then this is unbounded, so it goes to plus infinity. And so the only way this is 0, this limit is 0, is when the real part is strictly less than 0. So if we go in this direction of the proof, then if every solution holds this property, then in particular it holds for the eigenvectors of the eigenvalues, and then it follows that the real part of those eigenvalues are negative. So with this, the forward part of the proof is completed, and then the other implication, this implication, follows from a known property of exponential of matrices that tells exactly like this, that the eigenvalues, let me write it down here. It is another property. If all the eigenvalues have a real negative part, then 0 is an attractor, which means that for every solution, the limit as t goes to plus infinity of the norm, from without a norm, it's the same, it's equivalent, is 0. So this is by definition. This one is a non-property, like a characterization of the attractor 0. And this is even in both directions. So this easily proves the other implication. And so this, I think this is everything that we needed to review today. As always, if you have any questions, you can write it down in the comments below. I will try my best to answer them. Also, if you are interested in another topic that you would like me to cover, even if it's not from differential equations, I can try my best to answer that, and I will work on that. So good night to everyone, and see you around.